We're now going to look principally at matrices. And you notice up to this point, we really haven't had a lot to say about matrices in and of themselves. Okay, we've developed a whole mess of mathematical machinery for vectors, right? We have a vector space and we've developed all these results. But matrices actually are important outside of linear algebra. There are a lot of matrices that occur in contexts that have nothing to do with linear equations. For example, when you look at the covariance matrix, okay, it has nothing to do with the solution of a linear equation. And so matrices are important to study in their own right, and the proper way to study matrices mathematically is to think of them as linear transformations. And so this is how we're going to approach matrices. What is a linear transformation? Well, a linear transformation is a mapping. It maps one vector space, we'll say V, to another one, W. And we're just going to assume, for the sake of simplicity, these vector spaces both have the same field F. And this mapping isn't arbitrary. It has to satisfy the condition that it basically distributes over linear combinations. And this is what makes it linear, okay? So we say that the transformation of a linear combination is a linear combination of the transformation. Notice that scalars factor out of linear transformations, okay? And linear transformations distributed over sums of vectors, okay? Now, there's a very important fundamental property of a linear transformation, and that is that it always has to map the zero vector in its domain space to the zero vector in its range space. And you can actually prove that. And it's not a bad exercise to prove from the definition of linear transformation that it always has to map the zeros vector to the zero vector. So what is the significance of linear transformations? Well, they're important for many different types of operations. We're going to see three of them, but there's actually a large number of things that transformations are used for. Anytime you do any sort of signal or image processing, it's almost always the case that you have some sort of linear transformation involved. But the direct relevance to us comes from the fact that matrices are linear transformations. If you think about it, an m by n matrix, it maps Rn to Rm, right? And it turns out actually that this is a little bit of an if and only if statement. You can actually show that every linear transformation between two finite dimensional vector spaces can always be represented as a matrix. And conversely, any matrix is a linear transformation. And that's kind of obvious, okay? Okay, so what are some of these things that we can do? Well, first of all, we can do trivial transformation. We can do the identity map that maps each element to itself, okay? We can also do another trivial transformation, which is the zero map. We can map every element in the domain space to the zero vector in the range space, okay? But most transformations tend to have a geometric flavor. So the one thing we can do is we can do a dilation. We can take a vector and we can map it to some scalar multiple of itself. Okay? We can also do projections. We can do rotations, okay, which are actually kind of hard to do in higher dimensions. And finally, we can do coordinate transformations, which we called before rigid rotations, okay? Now it's kind of interesting to ask, well, are translations possible to be represented by transformations? And the answer is no, because remember what we said, the fundamental property of a linear transformation is it has to map the zero vector to the zero vector. And a translation, unless it's a trivial translation, will never map the zero vector to the zero vector. Okay, so translations are the one exception. They're actually another type of transformation called an affine transformation as opposed to a linear transformation. An affine transformation is just a linear transformation plus an added vector. The first type of transformation I want to look at is that associated with a projection matrix. And we've talked a lot about projections, but now we're going to show how to do them in a sort of general way. So let's suppose we have some vector v, and we want to find its projection onto a given subspace, just like we found the projection of the right-hand side vector b onto the column space of A. What we're going to do first, and this is important, we have to have an orthonormal basis for the subspace. So we're going to assume that u1 through um are unit vectors that are a basis, and they are all orthogonal to each other. That's what orthonormal means, basis. Okay, now what we're going to do is we're going to construct a projection matrix, and it's going to be equal to u times u transpose, where u transpose is the column vectors of u. Okay. And so here's the picture. We've kind of drawn this before. We have u, we have some vector. This should actually be v. Sorry, I didn't mean to make that u. So let me change that to v. Okay, and then I have my subspace spanned by the basis vectors, and so I'm going to project that down. Okay, and that's going to be the projection onto the subspace. And so that black arrow on the yellow subspace is what we get when we act on v with this projection matrix. Okay, now another thing we're very much interested in doing sometimes is reflecting a vector about again another vector. So let's suppose, for example, we want to reflect x about the vector v. Now we notice something, that this is the vector we want. Okay, so x and its reflection are symmetric about v. Okay, and we can go a little bit further by noticing that if we decompose x into its projection onto v and its orthogonal component, okay, then we notice when we reflect v, the reflection is that same projection along v, but we've reversed the sign on the orthogonal component, the component that's orthogonal to v. And so we can actually write this like this. We can say that the reflection is equal to the projection of x onto v, and now we're changing the sign. That's why we have the negative minus the component perpendicular to v. And if you think about it, you can convince yourself that this first quantity is a matrix, and it follows exactly the specifications of a projection matrix onto a one-dimensional subspace. And of course, x minus its projection is the orthogonal component, and we change its sign, and when you do the algebra, you end up finding the following result. And this is the matrix that performs this reflection. And this has a name associated with it, actually. We call this a householder transformation. Okay, next we're going to talk about probably the most significant sort of transformation, linear transformation, which is a change of basis.